Okay, welcome back to your CNT 140, Chapter 4, LAN Wiring for Future Needs. In this chapter, we're going to be discussing the 100 and gigabit meg networking, the importance of category, enhanced category, whatever, cabling 4, 5, and 6, fiber and copper for the future, and then the future wiring. Now, it's been said that the only thing that remains constant is change in itself, and that's certainly true in reference to changes in computer technology. In many ways, the rate of change is also uniform, exponential. It almost seems that we have often heard that we have left normal historical time and are now living on internet time. Even so, it is possible to accurately predict the near-term future of LAN wiring technology. And one of the most interesting features of technological change in the computer industry is the steady progression of technology from experimental to leading edge, and then to widely be widely accepted. Now, while experimental technologies are quite divergent, those that are feasible eventually become the hot new technologies that define the true state of the art. And of course, a new feature or a capability does not immediately supplement or supplant the existing products, but eventually products with useful new features become more readily available at a reasonable cost. And at that point, standardization emerges. Now, whether formal or de facto, and the product becomes then more widely accepted. Now, picking the next wiring technology. The best emergent technology for your network is an exciting and potentially rewarding game. The game is really not in trying to guess which experimental developments will become accepted, but rather in observing which leading edge technologies have begun to be accepted, and then employing them in the future. The creation of recognized standards is the key to which technologies will be used in the future. In local area networking, we are fortunate because we must operate in a multi-vendor environment. So the need for interoperability means that we must have strong, internationally accepted standards for networking. Another fortunate circumstance is that no proprietary technology dominates that field. Many, if not most, of the technologies that have become widely used are a result of unprecedented industry cooperation through partnerships, consortia, and standards committees. In addition, because of the need of interoperability, standards tend not to change radically once they are implemented. This is particularly true of LAN wiring. You can expect your LAN wiring systems to remain totally usable over many years if your needs remain relatively constant. This is not to say that if you progress from simple printer and file sharing to high bandwidth graphic or video applications that you might not need to upgrade some network components. However, most LANs support organizations with relatively constant needs. For example, if you have a standard 100 base T network in place, you may reasonably expect it to remain viable for a number of years. On the other hand, if you're installing new network wiring, you should plan for the future. So for LAN wiring, the future is fairly clear. There will be a gradual move from the current 100 meg network speeds to gig networks, and soon to be 10 gig networks. There are even higher speeds in development. There may be no immediate need or budget to convert your entire network to gig, but you should probably not install any new cable that will not serve that speed. And you'll be surprised how quickly you'll develop a need for at least some of the connections to be gigabit. So how do you plan for the future? How do you put in a gigabit network? Should you use copper wire, or should you be considering fiber? Can you hedge your bets? Well, let's see. 100 and gig networking compatibility. If you are currently using a 10100 network or a 16 to 100 meg token ring, you may not be using LAN wiring components that will move you to higher speeds, such as gig, or you may be getting along or basically limping along on a 10 meg or current network. These lower speeds are much less demanding in their need for transmission media than the high-speed networks, such as fast Ethernet and gigabit. So for example, a 10 base T will run at a workstation to hub distance of 100 meters on Cat3 cable. Now if you try to upgrade such a network to 10 times the speed, however, it'll most likely fail. So gigabit network should be, gigabit network there would be basically impossible. So what you can do if you may need to upgrade to gig speeds, or what can you do if you need to go to a gig speed? The answer is to install a LAN wiring system that meets the performance specifications for the higher speed now. It'll operate very satisfactorily at the lower speed for the present, and it will provide additional service as you upgrade to higher speeds. One sure way to provide such a wiring system is to use the 568C standard for Cat6 or augmented Cat6, the AC. Even Category 5E wiring is designed to support full gig network speeds, and A6 and 7 will go all the way to 10 gig. At the same time, Cat 5E, 6, and AC6 and even 72 wiring will fully support lower network speeds such as 10100T or token ring and FDDI, as well as the intermediate speeds for ATM and fast token ring. For that matter, it'll also support voice ISDN, T1, E1 very nicely. Now the table here behind me shows we have a table that summarizes supported use of Cat 3 through 7 installations. True, Cat 5E, 6, and A6, AC6 and proposed Cat 7 wiring should be used for a single application, not shared between data and voice. For instance, if your needs are uncertain, you may wish to overwire your workstations by pulling more than one cable to each workstation location, much like we've been speaking about with your bid projects. However, the shielding between pairs in Cat 7 is so nearly perfect that it may be feasible to bend this rule and allow some diverse applications to share the same cable sheath. On the other hand, there is a school of thought that holds the total separation of voice and data facilities down to even separate wiring closets and equipment rooms. This certainly might make sense if your telephone system and LAN system are maintained by separate entities. Standard practices for telephone wire installation are much looser than the strict requirements for Cat 5e and 6 and higher data installations. Many LAN managers have had bad experiences when the two types of installation methods are mixed. However, if all your cabling is installed and or maintained by the same people, you should be able to ensure that the Cat 5e 6 wiring stays Cat 5e and 6. Ensuring the performance to Cat 5e, 6, A6, and 7 standards requires much more than just the category cabling components. Location, routing, and workmanship issues are at least as important. Now, these three issues are difficult to judge because they are related to the installation process, but you can buy the finest certified components and still have them installed incorrectly. And that is why we've devoted an entire part of this lesson to the installation of the wiring devices, or this book to the installation of the wiring devices. Now, the Cat 5e, 6, and A6 and 7 testing certification section. The simplest proof of 100 gig network performance is to connect your 100 gig switch hubs and workstations and basically see if they work. Unfortunately, many of us must install cabling systems long before we buy the first gigabit hardware. Even if high-speed hardware were to be installed immediately, the time to cure cable problems is during the build-out stage of construction, not after we move in. And really, for the most part, gig switches are very common in the workplace today. The solution now is to have the cable system tested and certified as part of the installation process. This testing and certification process is described much later in the book, but is summarized here. First, the first step in certification is to use the proper materials. All cables, jacks, patch panels, and user cords, connecting blocks, and everything should be certified to the proper category by the manufacturer. There is no major benefit to specifying all this by brand name unless you're using a particular manufacturer's connecting hardware system that may offer unique features. For a smaller installation of, say, 50 stations or 50 drops or less, it'll probably just raise the price and then narrow the field of bidders who can actually bid on your bid project. The second step is to use properly trained installers, particularly for the Cat 5e, 6, A6, and 7 installations. Several certification programs exist for cable installers. Bixby would be one of them. The vendor-specific programs generally emphasize a common set of workmanship techniques and are adequate training in most of the situations. You should not insist that installers be certified by a particular vendor unless you're willing to put up with the extra expense and aggravation of having such a policy. It is more important that each installer either be formally trained at a recent course or be closely supervised during the installation. A few industry-wide certification programs exist, including the Registered Communications Distribution Designer, programs like Bixby Incorporated, formerly the Building Industry Consulting Service, and the RCDD requires experience and successful completion of a test. Now, a Network Transport System Specialist program also exists, and there is now an installer registration program that does not require membership in the organization. Later on in Chapter 18, we can get additional information on training and certification registration. The third step is to individually test and certify each workstation link. The worst case link performance criteria and testing guidelines, so the 568C, are an excellent basis for certification. Each link should pass all the tests specified for the category of the installation, and you should get a printed report. Keep in mind that you will have to pay extra to have each link scanned. The equipment to perform the testing is expensive, and the installer will expect to be compensated. Now, let's talk about a great video game, the need for speed. So, why do I need higher network speeds? Well, the answer lies in understanding the increasing size of data transfers in the modern network. The common word processing tasks have modest file transfer requirements, even if files are maintained on a server. However, we are doing many more tasks than letter writing today, and these new applications have placed great demands on our network transfer rates. For example, the average user today accesses graphics-rich internet websites, and often with audio and video multimedia content. We routinely attach fairly large documents such as Word documents and PowerPoint files in our emails. Another example is today I try to back up 30 gig of data to my home drive before I prepare to leave for the summer. And the estimated wait time over a wireless connection was 3 hours and 30 minutes. I then plugged my computer into the wall port, which would then hook me up to the gigabit connection, and I was actually done my transfer files in less than 45 minutes. A great big difference. Now, businesses are increasingly putting voice traffic onto our digital networks, and applications such as video, teleconferencing, telemedicine have high constant bandwidth requirements. In fact, digitized X-rays and CT scans are routinely being transmitted over the networks of medical providers. Many cities now offer real-time video of roadway traffic, and broadcast television and entertainment performances are following in behind. Now, so how much bandwidth is needed for efficient networking? Well, that depends on the application and the perception of the user. The chart here behind me shows some comparative applications and the amount of bandwidth that each would need to complete its transmission in 1 minute. Now imagine staring at your computer monitor for 60 seconds while you're waiting for this application to load. It'll seem a lot longer than you would normally tolerate, at least without some choice words under your breath. Now you can also scale the numbers a little bit to bring them into the reality of your network. For example, if the magazine clip were only 10 pages, it would need 40 megabits of network bandwidth to load in 1 minute, or it would need 240 meg per second to load in 10 seconds, which would be much more tolerable. However, do you have a 100 meg network now? What impact does devoting 40% of your network speed to one transfer have? The generally accepted utilization limit over Ethernet network is 60% to 70% utilization. So the 40 meg transfer would eat up about 2/3 of your network capacity, and the 240 meg would chew out about 30% hunk of a gigabit Ethernet pipe. So really, how are we going to get this information? A lot of it has to do with the media itself. So the importance of the category or the category cable, 5, 5E, 6, 6AC, 7. Installing cabling and components of the proper category is important for future upgrades in the data rate of your network. However, network data rates and cable bandwidth do not directly correspond to each other. Data rates, of course, are given in bits per second, typically in megabits per second, or even gigabits per second. Cabling components, including the cable and the connectors, are specified in terms of useful bandwidth in hertz or cycles per second, typically in megahertz or gigahertz. Data bits are usually encoded in a way that reduces the actual bandwidth requirement for a given data rate. For example, 100 meg fast Ethernet requires about 30 megahertz of bandwidth because of the encoding. Similarly, ATM 155 uses an encoding technique called Cat64 in order to place 155.52 meg per second on the cable at less than 30 megahertz. This is the reason that some data networking standards can operate at much higher data rates than would seem to be possible, given the cable's nominal bandwidth. Thus, we can put a 1 gig or 1,000 megabits per second data rate over cable that is rated for 100 megahertz on each of its 4 pairs. Now, this is no easy feat. The interface and digital signal processing circuitry to accomplish this with copper wire is very sophisticated. Any minor disturbance in the cabling components can cause such a data link to fail, and that is why it is so important to use the proper category of components for the application. Now, the table behind me shows the improvements that have been made to cable specifications to enhance the data carrying capacity. The introduction of Cat5 expanded the useful operation frequency or bandwidth from 20 MHz to 100 MHz. And then the TSB95 added testing requirements for older Cat5 links to near 5E performance in order to predict possible operation of gigabit Ethernet. Now, although the base bandwidth stayed at 100 MHz, Cat5e increased the next isolation by 3 dB, incorporated the power sum requirements for multiple disturbers or transmissions on more than one E pair. It added far-end crosstalk requirements, added propagation delay and skew, and added return loss to the more modest Cat5 parameters. The Cat6, A6, and Cat7 increased working bandwidth to 200 to 350 and even 450 megahertz. You may have heard these numbers as 250, 500, and 600, but those are the required test limits. The attenuation to crosstalk ratio must be positive to the lower frequency limit, and that is the generally accepted measure of the useful bandwidth of cables and connecting hardware. Some Cat7 hardware actually exceeds even the 600 megahertz specification. Some of them actually more than double it, and this may be subject to future standards in the making. So let's talk about the enhanced category, like Cat5e. Okay? The categories and classes of operation of the International Cabling Standards Organizations specify minimum performance parameters for cabling, components, and links used in structured LAN wiring. It is the purpose of the standard to set electrical characteristics of the wiring system without regard to the particular type of LAN network technology that is used with the cabling. Each of the category specifications, in reality, has been targeted at the operating requirements of a current or anticipated LAN topology. Consequently, Cat5 conveniently handles fast Ethernet. Cat5e handles gigabit Ethernet, 4-pair simultaneous transmit and receive, and Cat6 handles the 2-pair transmit, 2-pair receive of gigabit, as well as ATM 622 and 1244, the OC12, and the OC24 rates. The AC6 can handle 10 gigabit Ethernet and fiber channel just barely, and Cat7 can do 10 gigs sitting down without a problem. With those technical guidelines, each category class allows a wide range of applications, in addition to the classic Ethernet ones. However, it is quite possible and probably desirable for a manufacturer to build cabling components that actually exceed the minimum specifications of a particular targeted category. For example, at one time, Cat5 was considered the ultimate and was a manufacturing challenge. Soon, the leading manufacturers discovered that they could use innovative designs and production methods not only to comply with Cat5, but to actually exceed the parameter requirements, often by a significant margin. These better quality cables and connectors were initially called Enhanced Cat5 and ultimately were found to be all but necessary to achieve gigabit Ethernet operations. Now the same has happened with Cat6, resulting in Augmented Cat6 or AC6. Some exceed Cat7 preliminary specs by more than double. Now the lesson here is that good engineering can create components that have better performance and the standards than the standards actually require. Now can you benefit from those enhancements? Well, yes, particularly if you operate near the limits of distance or data rate. Better still, you may be able to plug in new technologies that were not even dreamed of when the cable standard was defined. Those of us who specified Enhanced Category 5E were rewarded with the ability to jump to gigabit Ethernet over copper as soon as it became available because our cable already met the TSB95 and or Cat5e performance levels that were later made part of the B standard. By the same token, enhanced cable and components for Cat6 and 7 already exist and may well prove to offer more long-term stability as well. You should buy the best cable and components that you can afford, keeping in mind that the network technologies of today are transient and will be obsolete in just a few years. Stepping beyond the envelope may be a little risky as some predicted technologies never reach critical market mass. So try to plan for 1 or 2 steps in increased network speed and then leave the rocket science for the experimenters. In that way, you'll have a network infrastructure that will provide optimum performance at minimum cost with a reasonable useful life. So now let's look at fiber optics, or bringing fiber to the front. The importance of fiber optic cable cannot be overemphasized. Fiber cable has unique characteristics that make it suitable in many types of high bandwidth, high interference, and interbuilding applications. As recent very high-speed technologies have emerged, fiber interfaces have been developed and marketed considerably in advance of their copper counterparts, whereas copper cables are limited to 100 meg for almost all applications. Above 100 meg, such as short distance is trivial for fiber optics. Although structured standards still spec the 100 meg limit, it will be just as practical to double or triple the distance limit for even the most rigorous high-speed network requirements. Not only has multi-mode fiber been available to handle 100 meg and gig, but it can also support multi-mode 10 gig at over 300 meters. And single mode fiber can go to 10 gig at 10 kilometers, which is 6 miles. So fiber connectivity technology has been refined to greatly reduce interconnection losses and to minimize reflections at the connections. Now this means that systems that use full duplex transmission reception on each fiber are feasible and that the fiber may be used in critical applications such as TV with minor reflections, where minor reflections can cause serious problems. In addition, quick connect fiber connectors are being offered that decrease the costs, the assembly, labor, and required training for a fiber termination. Now the popular 560AC standard still requires that only 2 cables to each only 2 cables to each workstation, and one must now be Cat5e or above, and it's presumably targeted for conventional telephone connection, either analog or digitalized DM. The other cable may be Cat5e or better, or it may be an accepted fiber. So why not choose both? Until IP telephony is in widespread use, you'll probably still need to provide the Cat5e or better cable for telephone use. But why choose between copper and fiber for your data? So here's an ideal scenario for LAN wiring for your future. Run 2 Cat6 or Cat5e or AC6 cables, and a 2-pair fiber optic cable to each work area outlet. You could actually use a fiber cable with one multi-mode pair and one single mode pair if you really wanted to be ready for future applications. Or you could use a 62.5/125 pair and a 150/125 pair, both multi-mode. Fiber core specs are critical in multi-mode fiber. You can get a 50U core fiber can handle greater speeds at the same distances or the same speeds at greater distance. It never approaches single mode, but makes 10 gig at 100 meters practical, and a gig megahertz at 300 meters, basically a snap. Use a modular 4-jack connector plate. Now you have 2 copper cables, either of which can run virtually all voice and high-speed data technologies, and you have the flexibility of using fiber or high-speed data or even video. We'll go into that a lot more in Chapter 11 when we talk about fiber cabling. Fiber optic cabling is clearly in our networking future. So what is the future of copper cabling? Well, in a paraphrase of Mark Twain, the report of the demise of copper wire is greatly exaggerated. There has been a great deal of press for several years that copper wire cabling should be abandoned in favor of either fiber optic cabling or wireless networking. Now, while the claims of the proponents are not without merit, they are also not unbiased. The latest supporters of copperless networking are the companies that produce those competing technologies. It is only natural that they would see their product as being technologically superior to older methods. Truth, as often is the case, probably lies between the extremes. There is a certain philosophical attractiveness to alternatives for copper wire. The fiber alternative offers a considerable increase in bandwidth, which translates to an increase in LAN data rates. Unfortunately, it may come at a greater cost and more limited flexibility. No one would argue that it would be difficult to adapt the hub, patch panel, and workstation outlet to fiber. Fiber has its own set of installation and testing difficulties, in addition to a higher component expense. Most of your existing network equipment would have to be scrapped and replaced with optically interfaced equipment and adapters. Advantages in one area may be disadvantages in another. For example, the voltage isolation inherent in fiber optic cabling would make it impossible to centrally power telephone instruments, so communications could not be maintained in a power outage. The solution for the time being is that fiber has an important place in telecommunication systems, but it will not immediately supplant copper wire as the cable of choice within our buildings. If one must choose between the two, fiber will continue to provide inter-building links between far-flung hubs, and links needing greater bandwidth distance performance than copper can provide. The wireless alternative is an intriguing one. It eliminates the need for any direct placement of cable, whether copper or fiber, and it is heavily promoted as the future of networking. However, it has some inherent disadvantages as well. The first disadvantage is that it knows no bounds. That means that your network connection signal can travel far beyond your immediate office, even outside of your building. Not only is the signal transmitted where it is not wanted, but the wireless LAN adapter is also susceptible to outside receive interference. Second, as more and more wireless devices are placed in close proximity, close can be hundreds of meters in distance, more interfering signals, clashes can occur. Do you remember the early days of cellular radio when the service actually met its claims of clear, interference-free communication from almost anywhere? The addition of thousands of users has greatly degraded the quality of reception. The same degradation can happen to crowded wireless LANs, except that the interference cannot be heard. It simply slows down the network in silence. The third disadvantage is troubleshooting and management. A direct cable network is easy to manage and repair. Most modern hubs, problems in the network cabling are easily isolated to one station, and monitoring of the process is very straightforward. Finding a radio frequency problem in a random deterministic virtual network is a much more challenging task. Fourth, wireless networking is more expensive in relation to direct cabling. Wireless network adapters are still usually 2 to 4 times the cost of copper cabling systems, including the copper adapters. Wireless networking, however, has a clear advantage in places where running cable is impractical, impossible, or basically just too darn expensive. It may be used as a very cost-effective link between buildings, especially across public rights of way. Practical or aesthetic reasons may tilt the scales toward wireless. For instance, a connection in a large arena or auditorium might be much easier to accomplish with a wireless link. Finally, if the workstation is mobile, wireless is crucial. Picture a forklift-mounted workstation with a network cable trailing along behind it. That doesn't seem very practical. We'll talk more about wireless in Chapter 13. So know the demise of copper wiring is not imminent, but neither does it meet all the possible needs. Each technology should be applied where it is the most appropriate and the most cost-effective. Then we have something called future shock or future wiring shock. Okay. Alvin Toffler in his famous work Future Shock, spoke of the pace of technological advancement as a shock to the individual and to society. In some ways, we in the computer industry have become accustomed to the rapid obsolescence of our equipment and the methods. Computers, printers, and even network switches are relatively easy to upgrade or replace as they are movable objects, attached only by their wire connections. LAN wiring is more of an immovable object, fixed into place within walls, ceilings, and cubicles. So what can be the result when the irresistible force of change meets your wiring? How can you prevent this from happening? Well, one thing you can do is to plan for the future. Design new cable systems so that they meet tomorrow's needs as well as today's. If you're installing a 100 base T network, that means you should install a cable facility that can go to the next step, gig networking, 10 gig networking. If you have an existing facility, add category 6 or A6 cabling and hardware when you add workstation drops. Plan the additions so the old cable can eventually be converted to the new system. A graceful migration such as this can be accomplished over a period of time to minimize the budget impact. Proper planning can give a cable system an extended life. Providing for the future may cost a little more now, but it will simplify change when it eventually comes. Now we need to talk about the tubing pull. In some ways, it is impossible to predict every twist and turn technology will make. It will be nice to have some way of replacing the wiring periodically if needed. You might need to upgrade to fiber optic cable. Maybe each workstation will need another cable and outlet to add an application such as video. What if you could simply go to the telecommunications room and pull in some new cable? It may be possible to do just that. A technique that works well in closed ceiling buildings can be extended to a conventional grid ceiling building as the building is constructed. Continuous plastic tubing home runs are made from the telecommunications room to flush-mounted outlet boxes at each workstation. A pull string can be blown through the tube or pulled in with a snake. The cable is then pulled through the tubing to the outlet and terminated normally on both ends. As needs change, new cables are pulled through the tube using the old cable as a pull string. One type of compatible tubing is called the 3/4 inch flex in the electrical trades. Another thinner tubing is used in so-called blown-in fiber installations. This method works well in closed construction, which is very expensive to rewire. It also works in smaller offices where the cable runs are not too long. It may have a special advantage for Cat 5e, 6, AC6, and 7 runs, as it avoids the performance robbing problems of kinks, minimum bend radius, tight tie wraps, and metallic runs along pipes and structural steel. Now that concludes our chapter Chapter 4 for planning on your wiring for the future and wiring shock, which is the fast advancement of our technologies, which we just covered. So be sure to go and do your quizzes for Chapter 3 and 4, and I will see you in class.